Hello, welcome back to the probability class. Today we'll study conditional probability. First, let me bring out the PPT. Yeah, here it is. This is the topic. What is conditional probability? It's evaluation of probability when either some information is known about the outcome of the random experiment or the experiment is performed under certain specific condition. There are many examples from practical life. Let's examine a few. If I ask you, what's the chance of having a rainy day without giving any information? That means, what's the chance of getting rain on a randomly selected day? The day may be anything from 1st of Jan up to 31st of December. However, if the question is, what's the chance of precipitation in Mumbai on a randomly selected day in July, then it means your interest is not about any random day, but on a randomly selected day in July. And typically, that's the monsoon season. So the chance of getting a rainy day in July is a lot more than overall chance of a rainy day calculated throughout the year. So you see here, the condition is given that it's a randomly selected day in July, and you are trying to compute or find the probability of getting a rain, having rain on that day. Similarly, chance of cardiac arrest for a 50-year-old obese man. Here, a specific group of people is given, not the whole population. What is that specific group? The group of people who are, number one, at least 50-year-old or 50-year-old, and number two, they are obese. That means they are overweight. So what's the chance of cardiac arrest for this group of people? Another example, suppose you come to a bus stop and you have been waiting for the bus for the past 5 minutes. What's the chance that your bus will arrive in the next 2 minutes? Here, what's given is you have already been waiting there for last 5 minutes. Fourth example here, we all know what we went through during the COVID pandemic, and the pandemic was really bad in India during the summer of 2021. Normally, if somebody has fever, say for example, in the pre-COVID days, there was no existence of COVID. So if someone had fever, then there was no chance that the person had COVID. And even these days, we are standing now in August of 2023. If somebody has got fever, the chance is very less that the person has got COVID. However, during the period of summer 2021, if somebody had fever, then chance of getting COVID was a lot higher for that person. So again, we are talking about conditional probability here. The chance of COVID infection for someone having a fever during summer of 2021. That's a conditional probability statement. Now let's come to mathematical setup so that we can handle problems. Let's consider the random experiment of throwing a die. And two events A and B are as follows. A is the outcome is odd, and the event B is outcome is less than 4. Now suppose it's like this. Someone is actually rolling the die and we cannot actually directly see the outcome. But the person tells us that what's the outcome. Now, when the die is thrown by that person, and if the person tells us that event B has occurred, then what do you know? B means the outcome is less than 4. So given this information that B has occurred, we are sure that the outcome is one of these three numbers, namely 1, 2, 3. Now, under this given information, remember the setup. We cannot see the exact outcome. Now, given this information that the outcome is either 1 or 2 or 3, if we are supposed to find out the chance of A being satisfied, then how much should the chance be? Let's see. How much should be the chance? So what's A? A is 1, 3, 5. It's given that this event has occurred. Now, if we are to find the probability that A has occurred, when will A occur? Given that B has occurred, given then B, given this, that means 1, 2, or 3. That's the outcome. Outcome is one of these. Under this condition, when will A occur? A will occur provided the outcome is either 1 or 3. See, if the outcome is 2, then A has not occurred. So given this information, A would occur provided the outcome is one of these. So here, what are the outcomes favorable for A? Favorable outcomes. These are the favorable outcomes for A. And what are the possible things? Given that B has occurred, possible outcomes are 1, 2, or 3. And what should be probability? Probability, we know, is defined by number of favorable outcomes by total number of possibilities. So it should be equal to 2 by 3. Right? That's what it should be. That's the motivating example. Let me clear the board now. And this is the thing we talked about. A and B are identified. What is B that's given, etc. This slide we worked out. Now, this is the notation for the probability of A given B. Probability of A given B is written as this. P of A line B. And it is to be read as probability of A given B. So in the earlier example, how much did you get as probability of A given B? In the earlier example, probability of A given B, that was equal to 2 by 3. Right? So in that example, probability of A given B is greater than PA. The question is this inequality always true? That is, given the information, the probability increases? That's the question. The answer is no. In fact, you cannot say anything about the relationship. It may be greater than, less than, or equal. Here are two examples. Consider the event C is equal to 1, 2, 3, 4. Means for the same random experiment, the event C is outcome is less than 5. This is C. So if C is given, then what's the probability of A? Given C, we know the outcome is either 1, 2, 3, or 4. And given this information, given this, A would occur provided the outcome is A would occur, that means favorable outcomes for A. What are those? Those are 1 or 3. So given this information, A would occur provided the outcome is either 1 or 3. So what should be P of A given C? The conditional probability, intuitively. We are talking about the things intuitively so far. What it should be. We will define the exact thing in a few moments. So it should be favorable number of favorable outcomes is 2, and total number of possibilities, this one is 4, because there are 4 elements here. That means half. And you see, probability of A given C is equal to PA in this case. That's what. Let me clear this board. Now let's talk about this one. Consider the event D, this one. Now given D, when will A occur? A would occur, that is favorable to A. Which all outcomes are favorable to A now? Only 5. Given this event has occurred, A would occur if and only if the outcome is 5. So what should be P of A given D? That must be equal to number of favorable outcomes is 1 here, and total number of possibilities, this one is 3. Number of elements here is 3. That's why it is equal to 1 by 3. And as you can see, P of A given D is less than P of A. So by means of these examples, you can see the relation between P of A given B and P of A. What is PA? No condition is given here. That's typically called unconditional probability. This is conditional probability and this is unconditional. And the relation can be either greater than or equal to or less than. You don't know what will be the exact relation until you know which example you are talking about. So far, so good. Let's move on to the next screen. Here comes the definition. Probability of A given B is defined as this quotient. I'm just reading it out, and then I'll take the whiteboard so that I can write it down there. P of A given B is defined as probability of A intersection B divided by probability of B. In other words, this notation P of A slash B is equal to P of A intersection B by probability of B. Let me go to the whiteboard so that we can, yeah. Let me draw a simple diagram first. This is A and this is B. Remember the example that we talked about a little while ago of a die throw, and there we had identified A and B as we did there. Keep that example in mind, and then the definition should be clear to you. B, the event B has occurred, that is the event given. B has occurred. That means what? The set of possible outcomes can be anything here. Set of possible outcomes now is not whole of omega, but only B, because this information is given. Now, under this given information, when will A occur? A will occur if and only if, typically we write that thing as IFF, if and only if the outcome of the random experiment is in A intersection B, because outcome is one of the elements in B, and A will occur if and only if the outcome is here. This part is A intersection B. So this is the set of favorable outcomes now for A. Favorable outcomes for A. And remember our intuition, probability is defined as the number of favorable outcomes divided by total number of possibilities. So how should it be, or what it should be? That's why probability of A given B should be equal to size of A intersection B, because that's the total number of, size of A intersection B means total number of favorable cases divided by size of B, which is the total number of possibilities here. So P of A given B should be defined this way. And let's check whether the definition given earlier matches with this. Let me clear the board. P of A given B, as we saw, must be defined as divided by this. And this is nothing but, if we divide numerator and denominator by size of omega, then that is nothing but size of B by size of omega. In other words, okay, now look at the numerator. This one, this is what? This is nothing but probability of A intersection B, because probability of any event is what? Size of the event divided by size of the sample space. That's why this is nothing but P of A intersection B. Similarly, denominator becomes P of B. So this one, the way we have defined, actually matches with the intuitive definition. The intuitive definition should be this, and the way we defined is this, both the things match. Once you understand the intuition behind the definition, your ideas get a lot clearer, and that in fact helps you solving the problem, number one. And number two, you feel a lot better while discussing the theories of probability. So let me clear the board and go ahead. Here is another example. We are tossing a coin 3 times and considering 2 events, A and B. A is this one, that the second toss is tail. Second toss is tail. So A means the second toss is given to you, that is tail, and nothing is told about the first and third toss. So it can be anything head or tail. That way we get the event A by varying the first and third toss outcomes, anything between head and tail. So HTH, HTT, etc. These 4 elements. Now, what's event B? At least one toss is head. At least one head. There are 3 tosses, and altogether there are 8 outcomes we know. We know there are altogether 8 outcomes, or the sample space size is 8. And among those 8 outcomes, only one, namely TTT, that does not have any head. All the other outcomes satisfies the condition mentioned in B. So that's why B contains all the other outcomes, and it has actually 7 elements. 7 elements, right? So let's see what is A intersection B. A intersection B is nothing but, if you do intersection, then in the intersection, all these elements should occur, right? A intersection B should be equal to all these elements. Now, that means A intersection B size should be equal to 3. So probability of A intersection B, that should be equal to 3 by 8, because sample space size is 8. Now, what should be probability of B? That is nothing but 7 by 8. Why is it so? Because B has got 7 elements here, 7 elements, and omega, size of omega is 8. So this one you get. That's why probability of A intersection B as the ratio of these two numbers, sorry, not this. Probability of A given B is nothing but ratio of these two numbers, probability of A intersection B divided by probability of B. That means 3 by 8 divided by 7 by 8. In other words, 3 by 7. That's the answer. Clear the board. That's what is calculated here. Let's come to another example. 2 fair dice are thrown. You know what is a fair die? Each of the 6 sides is equally likely. If the sum is given to be, at least 9, this is the condition given to you. The sum is at least 9. Then what's the probability that the first one is more than the second? Remember, conditional probability is always about 2 events. We have designated them as A and B, but you may use any symbols, X or Y. X is given or Y is given, and you try to compute the probability of the other one. So we talk about 2 events. It's given that one of them has occurred, and we try to compute what's the probability of the other under those circumstances. So let's identify the two given events here. Sorry about this. Okay. So the event A, we are using the same convention as earlier, that whatever is given, we are trying to put that as B and the other event as A. However, you may use any notation as I told you. So what's A here? What is the thing that we are trying to compute probability of? The first one is more than the second. The first one, I repeat, the first one is more than the second. If the first and typical outcome is something comma something, if the first one is 1, can the first one be more than the second one? No. So this is never possible. If the first one is 2, what are the possible outcomes for the second one? Only 2 and 1. So that's why 2, 1 comes here. Similarly, 3, 1, 3, 2, and 4, 1, 4, 2, 4, 3, 5, 1, 5, 2, 5, 3, 5, 4, and 6, 1, 2, 6, 5. These are all the possible outcomes within A. So how many? Okay, we don't need to directly count the size of A. It's good if you already have counted, but we don't need to calculate the conditional probability. Let's come to B now. What's B? B is what's given. That means this one. The sum is at least 9. Again, let's do the mental analysis. Sum is at least 9. Can the first one be 1? Question mark. Answer is no, because then sum can be at most 7. The first one must be at least 3 in order for the sum to be at least 9. And in that case, the second one must be equal to 6. Similarly, the first one can be 4 and second one can be either 5 or 6. So we must include both the possibilities in the set B. And this way, we get all the elements 3, 6, 4, 5, 4, 6, etc. And when the first one is 6, then the second one can be 3, 2, 3, 4, 5, or 6. So 6, 3, 6, 4, 6, 5, and 6, 6. How many elements are there? Just convince yourself that there are 10 elements. 3, 6 is 1, 4, 5, 4, 6, 2. And then that way, 1 plus 2 plus 3 plus 4, that gives 10 elements. So size of B is 10. How about the intersection? Intersection, if you look at, then 3, 6 won't appear in the intersection, right? This is not in the intersection because the first one must be bigger than the second one. Similarly, these ones are also not part of the intersection. I'm talking about the intersection now, intersection B. Which all are the elements there? Let's observe which all are the elements of A intersection B. Their intersection is nothing but this set. Just convince yourself. The first one can be 5. In that case, second one can be 4, and the summation is 9. So this one is part of intersection. Not 5, 3, 5, 2, 5, 1. 6, 3 is also part of this intersection because first component 6 is higher than the second component and summation is 9. Similarly, this one, here the first component is greater than the second component, summation is 10, that is greater than 9, and this one. Altogether, there are 4 elements in the intersection. So how much should this be? After identifying the intersection, we know probability of B probability of A intersection B must be equal to 4 by 36 And probability of B is how much? Probability of B is equal to 10 by 36. Why 36? Because that is the total number of possible outcomes or the sample space size. That's why while computing P of A given B, we take the ratio of these two numbers and we get 2 by 5. Good. Let's go to the next screen. So by this time, you have understood what is conditional probability, what's the motivation behind the definition, and we have also seen some examples. Now let's come to independence. When do we call two events to be independent? Two events A and B are said to be independent if and only if probability of A intersection B is equal to PA multiplied by PB. What's the motivation for this? Independence. One way to look at it is, if they are independent, then probability of A given B, that should be same as unconditional probability. That probability of A given the information B should be as much as without given the information. Then we should call that A and B are independent. In other words, given the information that B has occurred does not alter the chance of occurrence for A. Right? So this should be the definition. Now, what does this thing mean? Let's consider that PB is greater than 0, because PB is equal to 0 is a trivial case, and we'll see that in that case also they are independent from the definition. But let's consider the general case when probability of B is greater than 0. Now, what does this thing mean? Because we don't have any trouble in accepting this one as the defining criteria. That is, probability of A given B is equal to P of A. If that is the definition, we don't have any trouble accepting this thing. Right? Now, what does this thing mean? This means, I'm just writing both sides implication to mean that it means probability of, okay, let me take some more space. Let me go here. Okay, no space is given. All right, let me. I thought that there is some space in the next screen, but there is none. So let me rewrite the thing here. Probability of A given B. What does this thing mean? That's what I was up to. That means P of A intersection B, I'm just rewriting this, is equal to P of A. And that is nothing but, by changing side of PB, that is nothing but this. You see, that's why we define independence as this thing. And please observe this thing that's equivalent to this. We have already seen that this one is equivalent to this statement. Similarly, this is also equivalent to this. The probability of B given A is same as P of B, because that means nothing but P of BA by P of A is equal to P of B. And by changing side of PA, we arrive at this one. So you have got the motivation behind this definition. Let's take this example. Toss a coin 3 times, and A is the event that the first toss is a head. Sorry, this one. A is the event that the first one is head. So A contains these 4 outcomes: HHH, HHT, HTH, and HTT. What's B? B is the event that there is at least one head in the second and third toss. That means between the last 2 tosses, there is at least one head. So all these 6 outcomes should be there. The last 2 can be either head-head, like this, or the last 2 can be head-tail, like this, or the last 2 can be TH. Last 2 tosses can be TH. And by combining with these possibilities in the last 2 tosses, either head or tail in the first outcome, we get all these 6 outcomes. Anyhow, just convince yourself that B is nothing but this set. Once you do that, how much is P of A? P of A is nothing but 4 by 8 is equal to half. And how much is PB? That is equal to 6 by 8. That is equal to 3 by 4. So what's intersection A of, what's intersection of the events A and B? That's nothing but HHH. What does intersection of A and B mean? That means the first one must be head, and there must be at least one head among the last 2 tosses. That's why it is HHH, HHT, and HTH. These are the only 3 possibilities. And we get probability of A intersection B is nothing but 3 by 8. Let's check whether the criteria for independence is holding. Probability of A intersection B is nothing but this 3 by 8. And how much is PA multiplied by PB? You should multiply half by 3/4, and that way you will get also 3 by 8. So P of A intersection B is nothing but PA multiplied by PB in this case. That's why the events A and B are independent. Now, I want you to observe something here. Calculation is fine, absolutely fine. Look, probability is a very intuitive subject, although totally mathematical, but there is a lot of intuition behind it. And to have the intuition, it helps you in analyzing problems and also often makes your calculations simpler. So what's the intuition here? Let's look at the events more closely. The event A talks about the only first toss. I repeat, the event A talks about only the first toss. And event B talks about only the last 2 tosses, namely second toss and third toss. The tosses are independent of each other, isn't it? Without defining the term mathematically, we know that the toss number 1 does not have any bearing with the outcomes of the second or third toss because they are separate things. I repeat, the outcome of the first toss must not have any bearing or any influence on the outcome of the second and third toss. It's very easy to accept that. In other words, these two events, A and B, must also be independent because they are coming from independent exercise of experiment or independent parts of the same experiment. That's why A and B must be independent. And C, mathematically also you have got the same thing. This intuition helps you understand the underlying thing a lot easier. Let me clear this writing now and go to the next board or next screen. Now, we talked about independence of two events. In fact, we can talk about independence when there are more events together. In other words, when we consider a collection of events, then also we can talk about independence of that collection of events. Let's define it. There are two definitions there. One is pairwise independence and the other one is mutual independence. We will understand both the things or both the concepts. First, pairwise independence. Consider a collection A1, A2 up to AN. Now, we will call this collection pairwise independent. Please understand the term pairwise independent, provided any pair of events from this collection is independent. In other words, if I take any two events, AI and AJ, I is not equal to J. That is, they are not the same event, right? Just to ensure that they are not the same event, we write I is not equal to J. We take any two events, AI and AJ, then they should be independent. In other words, P of AI intersection AJ should be equal to P of AI multiplied by P of AJ. And that should happen for all pairs of integers between 1 to n for every pair of integers I not equal to j. That means A1 and A3 should be independent, and so should be A2 and A8 and so on. That is the meaning of pairwise independence. Clear the board. Go to the next screen. Now comes mutual independence. What is it? We will call the collection A1 to AN again, the same collection, to be mutually independent. Here I want to tell you one thing. When I try to write independent, I use, while writing it in PPT, I use the Microsoft equation. And when I try to write independent, it splits it for whatever reason and writes like this. I tried many ways to correct that thing, but I couldn't do that thing. So please bear with me. It actually means independent, and T should be actually together along with this thing. And you will see this kind of spelling mistakes in some other places also, which is unfortunately not in my hand. I'm sorry about this. Now, let's come back to this. They are called mutually independent, provided if we take any sub-collection. I repeat the term sub-collection because this is the collection. If we take any sub-collection of this, then that should satisfy this equation. In other words, if we take any k number of events, k number of distinct events, how to make sure that they are distinct? By writing I1 not equal to I2 up to not equal to IK. If we take AI1 up to AIK, then they must satisfy this equation. And please remember, we mean for any subcollection. That means if I take A3, A5, and A6, then also it should satisfy. Also, if I take only A2 and A9, then also it should satisfy. It should be satisfied, and so on. So this is the defining criteria. Just let me read it out meaning wise. For any subcollection of events, probability of their intersection should be equal to multiplication of the individual probabilities in the subcollection. Left hand side is nothing but probability of the intersection, and the terms used on the right hand side, those are the individual probabilities of the members. And left hand side becomes multiplication of all these terms. Let me clear this drawing. Go to the next screen. All right, here it is. Mutual implies pairwise. In other words, if a collection is mutually independent, then it must be pairwise independent also. Let's see why it should happen. Consider any collection of events A1, A2 up to AN. And suppose it's mutually independent. That means what? If we take any subcollection of this, namely AI1, AI2, AIK, then that subcollection must satisfy this thing, right? That probability of the intersection must be equal to product of the individual probabilities. Product of the individual probabilities. Now, what happens if we take only two events from this? What I mean is, in this equation or in this identity, I can consider subcollection of any size, right? AI1, AI2 up to AIK. K can be any integer greater than or equal to 2. And my subcollection contains K many elements. Question is, what happens if I choose K equal to 2? In other words, choose a subcollection of size 2. Say, I choose only the subcollection AI1 and AI2. In that case, what happens to this one? That this one will mean probability of AI1 intersection AI2 must be equal to the right hand side. And it must happen for all I1 not equal to I2. And that's what is precisely the definition of pairwise independence. Because pairwise independence tells you that if you choose any pair of events, namely AI1 and AI2, AI1 and AI2, in that case, these two events must be independent. And that's what is happening. That's why whenever they are mutually independent, this implies pairwise independence. So we get this one. Mutually independent collection will always be pairwise independent also. Let me clear this drawing and move to the next screen. Let's illustrate the earlier discussion with the help of three events. So consider a collection of events A, B, C. There are only three events here in the collection. what does pairwise independence mean to this collection? If we choose any pair of events like A, B, then they should be independent. That's what is this equation. If we choose B and C, then probability of BC should be equal to probability of B multiplied by probability of C. And similarly, P of CA should be equal to PC into PA. So all these three things should hold. If we choose any pair of events here, then they should be independent. That's what is pairwise independence. Now let's come to the concept of mutual independence on this collection. That means what? If we take any sub-collection, then the probability of the intersection should break up into product of the individual probabilities. So let's first take sub-collection of size 2. What are the sub-collections of size 2? It may be AB or BC or CA. If you choose this one, then we must get this thing. If we choose this one, we also must get this thing. And for this sub-collection, we must get this one. There is also another sub-collection, namely the whole collection, which is A, B, and C, all the things put together. And if we take this sub-collection, then we must also get P of ABC should be equal to PA into PB into PC. This should happen. So mutually independent collection ABC will mean this thing. And you see, mutually independence demands more conditions to hold good. In addition to all these things, in addition to all the conditions in pairwise independence, you are also requiring this one. Then only pairwise independence will happen. Otherwise not. So what we saw in the last screen, you see here also that mutual independence is a stronger criteria. When that is true, if all these four conditions hold, then of course these three conditions also hold, and that's why mutual independence will imply pairwise independence for this collection also, which you have already seen in the last screen. Good. Let me clear this. And move to the next screen. Let's take this example. Toss a coin 3 times, and the events A, B, and C are: the first toss is head, that's event A, second toss is head, that's event B, and third toss is head, that's event C. We will find out whether these are independent, pairwise independent, mutually independent, etc. We will answer these questions. But before doing any calculation, let's observe certain things here. See, event A talks about only the first toss. Event B talks about only the second toss, and event C talks about only the third toss. And please understand that the tosses are independent of each other. Means here we, by independence, we mean that they don't influence each other. In other words, whatever be the outcome of the first toss will not influence the outcome of the second or third. Similarly, the outcome of the second will not influence the third or whatever happened in the first one. In that sense, they are independent. And events A, B, and C are relating to first toss, second toss, and third toss only. So you expect them to be independent also, right? Let's see whether that is happening or not. What is the event A? First toss is head. Means the first position must be head and the other positions may be either head or tail. That way you get these 4 outcomes as favorable outcomes for A. Similarly, for event B, the second one must be head, and the first and third may be anything. That's how you get this thing. And so for event C. What is event AB? AB means what? Both A and B must hold good. So both first and third toss must give us heads, and the second toss can be anything. That's how we got this AB is equal to this thing. Similarly, BC means both second and third toss give us head. So first one can be head or tail. That's how we got BC is equal to HHH or THH. Now come to CA. CA is equal to HHH or HTH. Because here for CA, both first and third toss must give us heads. And what should be ABC? ABC means all these 3 tosses, first, second, as well as third, must yield heads. So ABC means only one outcome, that is head, head, head. Now let's compute the probabilities. How much is probability of AB? AB means this event. And how many outcomes are there? Only 2. So probability of AB should be equal to probability of AB should be equal to how much? AB has got, the event AB has got only 2 outcomes and the sample space size is 8. So 2 by 8 means is equal to 1/4. How much is probability of A? PA equal to half. PB equal to half. So you see, this identity is holding. Both are equal to 1/4. Similarly, you can check that P of BC is same as P of B into P of C, and in fact, both are equal to 1/4. So is the case for P of CA, which will turn out to be equal to PC into PA. Now, what happens when you consider all these 3 things together? A, B, and C together. What is the event ABC? ABC event, we have already seen, is nothing but head, head, head. So how much should be the probability of ABC? That must be equal to 1/8, because there is only one favorable outcome here. That's why probability of ABC must be equal to 1/8. And all these 3 things, PA, PB, and PC, equal to half. That's why this identity also holds good. P of ABC is equal to PA into PB into PC. So what do you get? All these 4 criteria are satisfied. That means the collection ABC is mutually independent, and hence it should be pairwise independent also. So the collection ABC here is mutually independent as well as pairwise independent. Let me clear this drawing and let me move to the next screen. Okay, let's see this example, which is supposed to be only pairwise independent but not mutually independent. That's what the heading says, only pairwise. Let's check whether it is actually true or not. That will be a nice example, isn't it? By theory, we have seen that whichever collection is mutually independent, that must also be pairwise independent. And here is an example which says a collection which is pairwise independent but not mutually independent. Here is the example. A ball is randomly chosen from an urn that contains 4 balls numbered 1, 2, 3, 4. Actually, all the balls are identical except the numbers. These are the 4 balls. The balls here as drawn, they don't look identical, but never mind. Just assume that they are identical in terms of weight, shape. Shape is anyway round, and other things, say smoothness. So if you blindly pick up, then any or each of the 4 balls has got equal chance of occurrence. That's what is important. Each of the 4 balls must have same chance of occurrence. So you blindly pick up one ball from the urn and observe the number. So the outcome is anything, any number between 1 and 4. That's why the sample space is here is the set 1, 2, 3, and 4. That's the sample space. Now let's consider the following events. Event A is the set 1 and 2. That means the outcome is either 1 or 2. Event B is the outcome is either 2 or 3. And the event C tells the picked up ball is either ball number 3 or ball number 1. In that case, what is the intersection of AB? Intersection of AB is equal to this. Intersection of BC should be equal to only 3, and intersection of C and A must be equal to this. Let's check whether it's pairwise independent, these 3 events. We are considering the events A, B, C. Let's check whether they are pairwise independent. How much is PA? PA is equal to 2 by 4. That means half. Why 2 by 4? Because A has got 2 elements and the sample space has got 4 elements. So 2 by 4 equal to half. And so is probability of B and probability of C. So what do we get? We get probability of AB. Probability. How much is probability of AB, by the way? AB equal to this one, right? AB equal to the singleton set 2. That is, the event contains only one element, namely outcome 2. So how much should be probability of AB? Probability of AB should be equal to 1 by 4, because there is only one outcome here and the sample space size is 4. So 1 by 4. And how much is PA? Is half. So is PB. So we can say P of AB is equal to P of AB equal to P of A into P of B. We can say that because both PA and PB are equal to 1 by 2. So the product will be 1 by 4, and so is probability of AB. So we get this thing. Similarly, probability of BC will be same as PB into PC, and so will be probability of CA, PC into PA. That's why the events A, B, C are pairwise independent. We have already checked this. Now let's come to this one, whether they are mutually independent or not. Let me clear the board so that it becomes more legible. Now we have to show that it is not actually mutually independent. What is the event ABC? That is A intersection B intersection C. Is there any common outcome among all these 3 events? There is none. So the event ABC is nothing but the null set. So probability of ABC is equal to 0. We know that the null set is the impossible event and the probability of that is 0. So probability of ABC is equal to 0. However, probability of A is equal to half, and that is same as probability of B, and that is same as probability of C. So when you compute PA multiplied by PB, multiplied by PC, that gives us 1 by 8. So this is not same as probability of ABC because that is 0. So here, this condition, probability of ABC is equal to PA into PB into PC, that condition is violated. So we can tell that this collection ABC is not mutually independent. So we have got a nice example. This example is of pairwise independence, but not mutual independence. With this, we come to the end of this session. Thank you for listening and see you in the next class.